All right, so in this module, we're going to be looking at dealing with exceptions and writing assertions. So the whole point of this module is to give you a little bit of a grounding in how Python and many other languages likes to deal with error conditions. And I'm sure that you've probably seen a few already. Initially, when you start to see exceptions and the way they control your program logic, it can appear a little complicated, or maybe even overly complicated. But it turns out that exceptions, using them properly, um, can greatly reduce the complexity of your code, and give you a lot of flexibility on how you handle error conditions, whether they be erroneous data that the users typed in, maybe something that you expected to find in a data file but you can't find, pretty much anything that goes wrong. Okay, so first question, have you seen this? Have you seen things like name errors, zero division errors, indexing errors? If you've been working with lists and tuples and strings, I'd be willing to bet that at some point you've seen an index error. We all have. Value errors. All of these errors generally get printed out to the console, and then shortly thereafter your program crashes. So the word error appears at the end of each one of these, but really what they are is exceptions. These are exceptions that are generated by Python, namely the function that we might be calling, or something internal in terms of the interpreter, such as trying to index something that's not available within a list or a tuple. So you've also seen, of course, what happens when an exception is raised. All right, so these error messages are generated from Python, and the default behavior when they are raised and you don't handle them is for your program to crash. Right? But the thing that we might not have been aware of up until this module is that we actually have the ability to catch these, or to kind of contain these exceptions and keep our program going. So if we write our program so we're prepared for these type of errors, our program can either generate a little bit nicer error message and then terminate normally, or possibly actually take some corrective measures and do something about the error. So again, learning how to capture these exceptions is really helpful. So what are exceptions? Exceptions generally are errors, but I think, as you probably know by this point in the course, there's a lot of different things that can cause errors. Sometimes, unfortunately, we have programmer mistakes, right? We simply type the wrong thing, right? We typed the wrong variable name. We've got an index out of bounds, something like that, and it's just a mistake. Other times, there's nothing wrong with our program. We've asked the user for an integer, and they type in a decimal number, or they type in a string. Missing resources. So if we're writing a program that's relying on data coming from an input file, and that input file is not there, there's nothing wrong with our program, but we can't continue, right? That is an error or an exceptional condition. So the Python language allows you, and also it does it itself, to raise exceptions. So the term raise exceptions means, and by the way, in other languages, and you'll hear me say this, in other languages we say throw an exception. But the idea is that you're creating an error flag. Right? You're generating an error. So Python raises these exceptions whenever you ask it to do something that it can't do. And again, whether it can't do it because maybe your resource is not available, or because what you're asking it to do isn't even valid syntactically. If the exception is not handled, Python crashes your program, right? Or so the exception, they crash your program. Okay, so what are some more examples of errors? Right. So if we look at over here, we've got an x being assigned the value 5, and then I go and print y. And if this was my only part of my program, I think hopefully we all recognize that that's certainly going to raise an error. What you'll see on the console is actually a name error. It says, okay, well, I don't know what the name y is. It's not bound to anything. This is one of those errors that, yeah, sure, it raises an exception. There's no need to try to handle your exception here. You need to fix your code, right? So this is a classic example of an error, a programming error, right? And so the resolution to this is not exception handling, it's fix your code, right? It's print X instead of print Y. Likewise, an index error. Most of the time, this is really just a matter of fixing your code. So if you see an index error printed out to the console and your code crashes, what we're about to see in terms of catching exceptions is probably not what you're really looking to do. What you're really looking to do is correct the fact that you're trying to access, I should have wrote my list here, sorry. You're trying to access my list index 3 and there's only 0, 1, and 2. Right? So again, in this case, you need to fix your code. Here's a case where it's much less clear. Okay, so how about opening a file that doesn't exist? Say your program relies on input coming out from myfile.txt. If that's the case, if that file does not exist, you're going to get a file not found error. And when you get that file not found error, your program, in this case, will crash immediately once you try to access the file F. Now, this really isn't a programming error, right? It's something that your code should be able to detect and actually maybe tell the user that the error is missing, the file is missing, maybe even perhaps ask them for the location of the file, maybe a different file to read something from. You get a lot of different options as to what to do. So here we're going to see actually the syntax for handling this type of an exception and being able to react to it. So first off, we've got the same line of code. We've got f equals open myfile.txt. We're opening in read mode. And once that file is open, I'm just doing a kind of a standard print statement. Okay, the file's been opened, and I can do whatever I want with the data in that file from there. What I've done, though, is added 2 keywords, and basically I've made this code part of a block following a try keyword. The try keyword represents a block of code that we're expecting or we're acknowledging that there's a possibility it could throw an exception. And directly following the try block of code, these 2 lines of code, right, whatever's indented under the try, is an accept block. Right? And this accept block names a particular type of an error that basically you're defining an error handler for. Right? So if at any point in time one of these 2 statements, and of course it really is going to be the open statement, happens to raise a file not found error, if that gets generated inside this try block, the code inside the accept handler will be executed immediately. So let's kind of walk through the logic here. Code that could raise an exception is put into the try block. If no error occurs, so nothing happens, myfile.txt does exist and it's no problem, then we can print, okay, open the file, all right, so everything behaves as normal. We skip the error handler, right? This is irrelevant because we didn't get an exception, so there's a file not found is not actually going to be dealt with. And we proceed. So from print OK, open the file, we're going to print done, right? So we proceed right out into try block, almost like this was an if and an else, right? Same idea. If the open method failed, if it raises a file not found error because myfile.txt is not there, maybe you don't have the ability to open the file, right? You don't have privileges to open the file. What's important to note is that the execution inside the try block halts, it stops. The print OK open the file will not execute. As soon as that exception is raised on that open command, the Python runtime system will jump you into the exception handler that you provided. Now, if this raised a different type of an exception, by the way, it would not be caught by this exception handler and your program would just crash. But since it's actually throwing or raising a file not found error, and you have an accept handler for that particular type of an error, Python will run your code here. And note that once the print sorry I'm missing my file.txt runs, I'm going to just proceed right back down to print done like nothing really ever happens wrong. Right? And that's the real power of exceptions, right? We can catch the exception, we can provide an error handler, have our code execute, and then carry along, right, if we wish. Now, it might be the case that we can't, right? Maybe there's really nothing to do if you can't open a file. Well, then we can just call exit, right? We can print out a nice message and call exit. Either way, it offers us the ability to more cleanly deal with the error condition. Okay, so why exceptions? Why doesn't the open command just simply return none or return some sort of a flag value that says, "Oh, I couldn't open the file"? What's the benefit of using these exceptions? And the most important part about it is that it allows us to write code to detect an error, but to have some other part of our code in our program actually handle it. Right? So, for instance, the open command can do a lot of work to detect the fact that the file does not exist, but it doesn't need to actually figure out what to do about it. It's not going to print out an error message. It's not going to exit the system or something like that. It's raising an exception, and somewhere else in our program, namely, on the slide before, I can have an exception handler that can figure out what to do about the problem. So this is really important. Often the code that detects the problem is not in the position to decide what to do. Namely, more important or more frequently, we'll be calling a function, and inside the function, we might be able to detect that an error occurred. But inside of the function, we don't really know why that function had been called, right? Most of the time we write a function, it's reusable. It's called many, many different times. And depending on when it was called, might require us to do something different based on that error. So a function that can detect that there's an error might not really know what to do about it, right? And exceptions allow us to handle that situation. So this is kind of a little bit of a trivial example, but it points out what I'm talking about in terms of a function detecting an error, but not necessarily dealing with what to do about the error. So I've got a function called quotient. It takes an a and b, a kind of a numerator and a denominator, and it returns a divided by b. There's a danger in this function, right? If b happens to be 0, that's going to throw an exception. That's a problem. We can't divide by 0 because that gives us infinity, and infinity can't be represented in a computer. So you might say, okay, well, I'll detect it. Right? And it's easy to detect the fact that b is 0. Now, we don't know what b is. We don't know what a is. We don't know why someone called the quotient function. But maybe it's user input, maybe it's not. But we know that b is 0. So we can detect that we have an error situation. If there is no error situation, it's very clear what to return, right? It's very clear what the action by quotient should be. We return a divided by b. But the question is, well, what do we do once we figure out that b is 0? All right? So if I'm writing a function, I've detected it, and I got to ask, well, what do I do? Well, one option is to just print out b is 0, right? And then quotient doesn't return anything. The problem with that is that you're making a user assumption. You're making an assumption that your program is being run sort of interactively, that the user's going to see this message, that somebody's actually even watching the output of your program. Believe it or not, most programs run in the background. People don't even look at the output. There is no output. The output actually goes to a text file somewhere, a log file. So, in the programs we've written so far, we're generally very anxious to find out what our program's going to say, right? We want to see whether it works. So we're paying a lot of attention to the output of our program. But in truth, that actually is a very exceptional case. Most of the time, there's nobody watching the output. So printing out b is 0 is probably going to be ignored, and it really isn't probably going to be very useful. And now the calling code, the code that actually called quotient, is going to get a return result back of none. We haven't returned anything. And if it doesn't properly check for that, that's going to cause some other sort of crash later on in our program. So we're basically just propagating that error. So another possibility is to just simply return something. Right? Maybe we can return 0, or we can return not a number, or none. Again, that assumes that the code that called quotient is going to look at that return message or return value and check for that error condition. You're forcing yourself, if you're the only programmer on the project, you're forcing yourself to write handling code every single time we call the quotient function to make sure that it doesn't return some sort of an error condition. Right? That's generally not a good idea, and it's going to lead to really buggy and complicated code. So the real solution here is to punt. Right? We don't know how to deal with this error here. There is no valid return value. There's nothing that makes sense to return implicitly. We don't want to necessarily print something out. What we want to do is we want to potentially crash the program unless somewhere in the program decided to handle this situation. So to generate an error, so this is different than the try except block. Right? To generate an error, I use the keyword raise, right? And I can pick an exception. Right? One of the built-in exceptions is zero division error, which is quite nice, and we can print a message inside the zero division error. And of course, here I could say that it was B. And at this point, quotient will no longer be running. Right? Quotient will no longer be running, and if quotient was called within a try block, then that error can be handled. If quotient was not called within the try block, then that error will actually crash the program, forcing the programmer, by the way, to now deal with that problem, to actually put in a handler if that's necessary. And here we see the proper handling of it. Okay, so I've asked the user for an x and a y, and I've called the quotient function inside a try block. Quotient may very well raise an exception, so I've done it inside a try block. If everything goes well and it returns a value, I'm going to print out the quotient, but if everything does not go well, I know that quotient will raise a zero division error. So the actual calling of this code is pretty clean and pretty uncomplicated. We've sort of got the happy path where everything goes right and we can put as much code as we want here. And then we've got the error path. If something goes wrong, and I guess that's probably the only thing that can go wrong with quotient, but if something goes wrong, then we can tell the user what happened. Finally, one last use case of exceptions, and then we'll sort of convert this to the idea of an assertion, is actually as a programming and a debugging tool. So we often write functions with expectations. And you'll see, the book uses this a lot. It says, okay, well, I'm assuming something about the input parameters. So my bulk multiply. I'm taking list 1 and list 2, and if they're of equal length, I'm going to multiply them together and return a new list, a new list with the product of each corresponding value in these lists. And so the assumption is list 1 and list 2 are of equal length. You can write that in the comments all you want, but you can't really actually make sure that that's the case. Well, you could, right? You could check it. And if that wasn't the case, actually raise an exception, right? So if the length of list 1 is not equal to the length of list 2, we could forcibly raise a value error exception, and that seems to make sense. A value error is one of the built-in exceptions for Python. And by the way, you probably want to consult the textbook and the documentation to see all the available exceptions that you can use. But I'm throwing this value error and saying the list must be the same length. So I've forced whoever called bulk multiply to deal with this problem if they don't pay attention to my comment. Right? So that's pretty good. It's a little bulky though, right? So I've added a little bit of a branch into my code. A more succinct way of doing it is an assertion. Right? So if you think about this, this is sort of like you check to see whether something's wrong, and if something's wrong, do something. An assertion basically is saying, I'm going to assert the fact that, and I actually need to write length here. This is an invalid expression. It should be length list 1 equals length list 2. I'm asserting that the lengths are the same. And if they are not, here's the assertion error that I want to throw. And this will throw an exception, and it'll say list must be the same length. Notice the syntax here with assert. There are no parentheses. This is not a function. This is a keyword. So assert followed by a condition, right? And again, this should be len list 1. and then what to do or what kind of message to throw if something goes wrong. And then from then on, we can just keep going. So assertions are really an excellent way of checking some of your assumptions, checking your parameters, or checking that something should be, or when we know that something should be the case, ensuring that it is before we go further. This is a much better technique than sort of just like kind of hand waving and hoping for the best, because when we hope for the best, we don't really have a lot of control as to what would go wrong. It's not as clear exactly, well, is it going to be a problem if list 1 and list 2 aren't the same length? It looks like if list 2 is too short, we would get an index out of bounds error. If list 2 is smaller than list 1, since we're looping over all the indexes in list 1, that might be a harder bug to find when that does happen. So in summary, we want to use assertions and we want to use exceptions in our own code to help us manage the complexity of error checking and error handling. Probably more importantly, we want to be comfortable with being able to use try blocks and except blocks to handle exceptions being thrown by Python code, right? So the built-in Python code, a built-in module that we might be using.